Vishnu has promised us lions tomorrow. So hopefully next year, maybe Subrat or someone else can promise us tiger or something. I'm going to be telling you about some work on QNEC bounds in CFTs basically. Much of the talk will be dedicated to holographic calculations, and towards the end I'll also talk about the CFT calculations a bit. This is largely based on this paper which we'll upload hopefully tomorrow night on the archive. But there were these earlier two papers which came out which were mostly quantitative calculations. This new one has exact calculations which will come out on Wednesday. The last part of the talk is mostly work in progress with Pratik Roy, who is a postdoc at Wales. Alright, so this is how I've structured the talk. I start with a brief motivation and introduction to the problem we were looking at. The first kind of setup that we look at is a global quench in a holographic CFT. And the section 3 here is some very new results. So I apologize if this seems a little half-baked because this was cooked up like 1 or 2 weeks ago with Pradeep. But I think this adds a bit of insight to the discussion, so I just included it. And I conclude with some PK directions. Alright, so let me start with a quick introduction. So the goal we are trying to achieve is to figure out some interesting bounds on CFTs or on critical many-body systems using what's known as the quantum null energy condition. I'll describe what this word quantum thermodynamics means. So quantum thermodynamics is a relatively new field emerging out of the quantum information literature. So people have tried to generalize ideas from classical thermodynamics like work, heat, and so on to quantum processes or finite dimensional quantum systems. So these are just some list of results which are interesting, which have been derived recently. So for example, people have tried to calculate how much work you can extract from a quantum state. There's a formal definition of quantum work, which I won't need for this talk. Then there is this nice set of papers which tell you that quantum entanglement can lead to weird heat flows. So typically heat will flow from a hot body to a cold body, but if the two bodies have some prior entanglement, you can have an opposite flow of heat.
Is this the thing called quantum energy teleportation?
I haven't heard this phrase before.
Because it's a different thing which is okay.
Could be, yeah, but most of all of these results are just for finite dimensional quantum systems. So it's just a few qubits or a few qubits and so on. So the goal is to kind of use these ideas of generalizing heat, work, etc. to many body systems or to CFTs in particular. So what will be important for the talk is this idea called irreversible entropy production. We've already seen this in our classical thermodynamics courses. So if you write down the total change in entropy in any process, you can decompose it into two parts. There's a reversible part, which is just heat exchange with the bath, Q by LT. There's an irreversible part, which I call delta S irreversible. And the second law of thermodynamics of the classical Clausius inequality will tell you that the irreversible entropy has to always be non-negative. People have written down a generalization for a quantum version of irreversible entropy production, and it takes the form written here. So this first object here is the relative entropy between these two states. The subscript E is some environment density matrix. Rho E0 is the initial environment density matrix. This I is just the mutual information between the system and the environment. S denotes the system. And I you can rewrite as a relative entropy between the full state and the product state. So just heuristically speaking, why do these terms exist? So the first term is due to losses of information contained purely in the environment. So I have a system coupled with an environment and I trace out the environment, so I lose information which was already in the environment. That's heuristically the first term. The second term is the losses you incur because of correlation between the system and environment. I'm tracing out the environment, so I lose some correlation. So heuristically, these
So can you just explain what the idea is? There's a system coupled to an environment.
Right.
And the whole thing is in a pure state?
The whole thing is in a pure state, but it could also be mixed. I mean, you need not assume that.
Okay, the whole thing could be in a mixed state.
But initially they are in a product state, so it's rho S tensor rho E.
And this S irreversible is the change in entropy of what? Of the system?
Sorry? No, this is the change in this is the entropy produced in the system.
In the system?
Sure, yeah.
I see. So the system entropy change is somehow, or depends on The environment density matrix. That's a little strange, right? But
No,
okay.
because there are two. I mean, it's a total irreversible entropy production in the entire process. You can't associate it to the system only.
I see.
So,
Okay.
So it's just a measure of how much information you lose essentially.
I see. If the whole thing, if system plus environment was in a pure state, then this relative entropy is also same as rho s and rho LC, right?
This one.
Yeah. If the whole thing was in a pure state, these two relative
But
entropies would be same.
after the process, they need not be pure anymore.
Oh, I see.
So imagine you have like rho e tensor rho s. You do some unitary which entangles them, and then you trace out the environment and you construct rho s and rho e separate.
I understand the first term is more. Why is the second term that I don't understand that at all?
Why is this term there?
Yeah.
I can't access the mutual information, right? If I trace out the environment, I don't have access to the environment. So I don't have access to the correlation between the system and environment.
And how is this a contribution to the entropy of the system?
No, it's not a contribution to the entropy. This is just the total irreversibility in the process.
Oh, okay, I see. So it's not like that.
It's not like the system gets this amount of entanglement inside it.
Thank you.
So what fixes this coefficient, for example, the rate coefficient between the terms?
Oh no, this is just a definition. I mean, you
Yeah,
could-
so how does one motivate this definition?
the way I'm saying, I mean, I want to measure how much irreversibility is in the
So
process.
if we put a 2 there in front of I,
You could put any positive constant. I think.
so it doesn't matter.
I think it
Now
should be.
this matters. So
I think it should be.
So for instance, if you did something to disentangle the system in the environment,
Hmm?
then the second term is 0.
Oh yeah, but this assumes the initial state is like like it's factorized initially.
Oh, initial state is disentangled.
Yeah. So it's a product state and then you act with some unitary or some quantum channel which are like.
Oh, I see.
Alright, so for specific situations when I have a unitary evolution of the initial states, so let's say U is some entangling unitary which acts on the system and environment together. If the system has a fixed point which I call rho s star, such that under this unitary the density matrix doesn't change. So initially it was rho s star tensor rho e 0 and it remains the same. If such a state exists, then the irreversible entropy production can be just written in terms of system variables. So this is just the difference between the relative entropies before the process and after the process. So for example, rho s stars could be like the equilibrium state and you achieve at the end of the process. So you couple the system and the path and let it evolve and it reaches some equilibrium. That's rho s star.
Wait, this is a property of both rho s star and rho e 0. It can't be a property of only rho s star.
Yeah, that's why I call it a global fixed point.
But you only use the system density matrix. Why didn't you write the environment density matrix?
Yeah. If such a state exists, you can simplify this expression down to just this expression.
Is it that rho e 0 is given as part of the definition of quantum mechanics?
Yeah, rho e 0 is some fixed reference state.
That's right.
Right.
I mean, if you have some sort of fixed point, it would be some fixed point of the coupled system, right? So rho SE.
Yes, but I'm assuming they're initially in a product state, so they remain the same.
So U is just factorized.
No, U is entangling, but suppose there exists a state such that if I add the unitary, they don't couple at all. Imagine two systems at the same temperature. There's no information for it. I mean, both are at equilibrium. There's nothing happening. So, rho s star you can think of as the final state you achieve after the process is done. So this object here is manifestly positive. So this just follows from the monotonicity of relative entropy. This is the relative entropy before the process. This is the entropy after the process. And relative entropy always decreases in any process. So it's clear that this irreversible entropy production is positive. But people have managed to establish stronger bounds. So people have found both a lower and an upper bound on this object, both of which are positive. The lower and upper bounds are related to some distance measure on the space of states. So it's like the fidelity. Not exactly, but it's similar to the fidelity. The question is, can we find similar bounds for many body systems, for a field theory? These exact objects in terms of the fidelity or some distance measures are very difficult to evaluate. I can't diagonalize or I can't trace out the quantum field theory density matrix and sit and evaluate these fidelities. So maybe there is a better way to find similar bounds. I won't be claiming that the bounds I find are the same as these bounds which are shown in the quantum information literature. But what we will find are upper and lower bounds on the entropy gradient. Right. So the main tool or the main condition that we use to constrain these systems are what is called the QNEC or the quantum null energy condition. So the setup we are looking at is a quench in a 1+1 dimensional CFT. So at some time u equal to 0, I suddenly change the parameter of this Hamiltonian, or I suddenly inject energy and momentum into the system. And the question is which such quenches are physically allowed, and by physically allowed I mean which quenches satisfy the QNEC, which do not violate the QNEC. The QNEC is this inequality. I'll denote the left hand side of the QNEC by this script Q. There are two of these, plus and minus, for two of the light bond directions. T plus plus and T minus minus are the two stress tensors. S is the entanglement entropy of some state. Del plus and del minus are derivatives of the entanglement entropy with respect to deformations of one endpoint. So I'll show you what I mean. So let's say I want to compute entanglement entropy of this interval, colored red in this figure. It's a 2D CFT, so it's just an interval in space. I can deform one endpoint of this interval along one of the null directions, let's say x plus, by some small amount th plus. And I can evaluate how this entanglement entropy changes under such a deformation. So I get del plus and del minus s as the derivatives under such a transformation. Interestingly, QNEC can also be written like this form here can also be written in terms of a relative entropy between the system density matrix and the vacuum density matrix. So rho r is any state you want to evaluate the QNEC in. Sigma r is the density matrix of the vacuum reduced to this interval.
So I have a question. So this is not the usual QNEC, right? This is the special 2D version.
This is only true for 2D
So
CFT.
the bottom one is that the usual QNEC or the special 2D version?
The bottom one is the usual QNEC, but the 2D CFT QNEC can be rewritten in terms of the usual QNEC.
Okay.
So you can do some conformal transformation and remove the S prime
Okay, so
square.
it's not a stronger fit.
Sorry?
So this is not a stronger
No, in
fit.
2D CFT this is equivalent to the weaker QNEC.
So things are different.
Sorry?
Things are different.
Yes, yes.
So things will be different if you were doing normal.
Yes, they would be different. Yeah. For instance, I don't know how one would define this null derivative.
Yeah, that's what I mean.
This is something we're looking at. I will say some words at the end. We're trying to see what this means on a spin lattice, for example. Right, so why should you believe QNEC? It has been proven in a variety of contexts. For example, it was first proven in free quantum field theories by Boson and many others, free bosons, free fermions, and so on. There's a holographic proof in holographic QFTs. There's an interesting proof in 2D CFTs by Balakrishnan and Faulkner. So the holographic proofs assumes something called entanglement wedge nesting, or essentially it just assumes that the bulk satisfies the classical null energy condition. The 2D CFT proof assumes that the state is cyclic in the algebraic sense, but I won't need to refer to this later. There's a proof based on von Neumann algebras and by Faulkner and Sehan. They prove this statement, or a slight generalization of this statement actually, for states which have finite average null energy. I'll define this later, and for states which have finite relative entropy. So to define the QNEC, first this object has to be finite, otherwise the derivatives make no sense. So they prove it for states which have finite relative entropy, and also they need to have finite average null energy. Right, so this was the overview, the main idea of the QNEC and so on. So the setup we are looking at is a holographic global quench. So by global quench I mean the entire system is shocked at the same time. So I inject energy and momentum in the whole system. It's not like I'm inserting it at one point locally. Sorry?
Is it uniform?
Yeah, it's uniform. Energy is injected across the board. So the setup is
It's a non-local thing.
yes. So the setup is I have an instantaneous transition between two momentum carrying thermal states. So in the CFT I have a thermal state which has some momentum, it's like a Gibbs ensemble. The dual is some BTC geometry which also has momentum. So in the dual, because of this transition, I have a null shock. So I have two spacetimes, a BTC and another BTC which I glue across a null shock. In the dual CFT, the stress tensor looks like this. So for u less than 0, it has some value Li. For u greater than 0, it has some value Lf. When these functions Li and Lf are constants, this is the setup I've described here. So this is gluing to BTC geometries across an null. But you can glue generic geometries. I mean, you can choose any arbitrary function Li and Lf, and that would be some kind of quench. So the holographic dual has this metric. It's ADS 3. Z is the radial coordinate. M would be the mass of the BTC if there were no shock, if there were no energy injection. J would be the momentum of the BTC if there were no quench. Z goes to 0 is my boundary. But because I am doing a quench, the M and the J have a theta function. So for u less than 0, I have these values for the BTC. For u greater than 0, I have these values. So F denotes the final state. I denotes the initial state. Right, yeah, so I said this. So M is like the mass of the BTC before the quench, and this is the mass of the BTC after the quench. This is the momentum before the quench, this is the momentum after the quench. So you can plug this into Einstein's equation and figure out which stress tensor works out. The stress tensor which satisfies Einstein's equations looks like this. This is exact, it's not quite a bit than Z or anything. It might look that way. Q and P, Q you can think of as heat injection into the CFT. P is the momentum injected into the CFT. Heat or energy injected into the CFT. So Q and P take these forms. They're proportional to delta functions because it's a null shock. So in the bulk, this u coordinate is null. At the boundary, the u coordinate is time. So which is why I have a delta u. So if you've seen ADS weather spacetime, this is just ADS weather, but the initial state is not vacuum, it's a rotating BTC. The final state is not a non-rotating BTC, it's a general rotating BTC state. So this is a slight generalization of the usual ADS weather. I'm not doing something crazy.
Of course, they're all local EDS.
They're all local ADS.
But just the way that they're default.
Yes.
That's why you can generalize media so easily, because it's all local areas.
That's true, yeah. And that will also be something I rely on for the entropy calculations, because I can uniformize each of the
No,
patches.
I think this trick at least for non-rotating works as I
The what?
This trick here for at least for non-rotating, this trick works for high
That you have you have a black hole and then you add some, you throw a shell into it.
Yeah, like
So you get a black hole with more mass.
yeah. You can, I think I believe I've done a calculation high dimension that also that this exact thing works.
I mean, Shiraz and then also did this for high
I guess it's
dimension.
like a Toff.
I don't think I'm the first one to do it.
It's the first, no, but maybe there's the first part of the Toff-Gray calculation. Rather than having two shells, you just have a black hole and you throw one more shell in. So maybe this is like the Toff-Gray.
One shell that comes to go to one and go back.
Yeah, so it's like the Toff-Gray solution.
May
Yeah.
Alright, so I've given you what the stress tensor of the dual CFT is. What I want to compute is the QNEC, which is this object. So I know this first one. What I would need to compute is entanglement entropies after the quench. So I'm quenching the system. So although the stress tensor looks like it's just the thermal value, so L is a constant. The entropy would not be thermal. The state is out of equilibrium, so I need to compute the entropy. So I need to compute S and take its derivative with respect to such a line deformation. To do that, I just do the HRT prescription in this setup. So this calculation was done a while ago by Hong Liu and collaborators, and also by Mukund Rangamani and collaborators. But this was only for non-rotating BTCs to non-rotating BTCs. If you add rotations, the thing becomes very messy, and you can't integrate the geodesic equations in BTC with rotations generally. So you have to rely on what we did, which is use uniformization maps. So as Costa said, the spacetimes are local areas, so I can uniformize them to Poincare areas. However, there is a shock, so I have to use two different maps. One map for the future spacetime, one map for the past spacetime. So I've just shown a schematic of what the spacetime would look like in Poincare coordinates. So this block on the left is the uniformized spacetime before the shock. So I applied some diffeomorphism, which is essentially a conformal transformation of the boundary, which takes the metric to just empty areas, to Poincare areas. And that's the left block here. The right block is the same, but I have to use a different uniformization. next I just want to shoot a geodesic for some boundary endpoints, let's say PL and PR. I choose an interval with these two endpoints. I shoot a geodesic and try and compute its length. So the geodesic will intersect the gluing surface, this null shock here, which is blue on the left geometry, red on the right geometry. It will intersect it in these 2 points, which I color red. These 2 points are not known a priori. I have to solve for them by imposing extremization conditions on the null shock. So these intersection points are solved for by imposing extremization at the null shock. Because I'm using uniformization maps, these equations reduce to some nice algebraic equations. So I can just use like a find root algorithm in Mathematica and expect some answer. Oh, I forgot to add certainties here, or it's not shown. So this should say lots of technical certainties which I'm skipping. So I don't know why I forgot to add certainties, but yeah.
So what are you optimizing, the length or the length and the surface at the same time?
Oh, so the fact that I map to Poincare coordinates, I know the geodesic in Poincare is semicircle. So the geodesic is extremal everywhere other than the shock.
Okay.
So I just need to ensure it's extremal at the shock. So for that, if you look at this baseline, it has these theta functions. So if you compute the geodesic equation, you get a delta function. You integrate it, you get some discontinuity in the tangents. So I just impose that the discontinuity is correctly accounted.
So, this interval is the future of the shock? Or?
Yeah, to the future. To the past, you just get the formula.
Yeah, okay. Wait, isn't this a shock coming in and then going out? So within the past, you should not get the formula.
It's not coming in. I mean, it's at some fixed time at the boundary. So at u equal to 0 in the boundary,
Oh, it's only going.
it's only going.
No, but you could trace it back, it could also have come in from the same.
It could also have come
If
in.
you trace the whole space-time geometry, it's going in, but if you evolve it in the past, it will also fall into the white hole. So you can think of it as coming from the white hole and
Oh, sure,
falling
you
into
can.
the black hole.
Sure.
You're just choosing to trace it.
We just choose, yeah. Right, so as I said, I'm skipping a lot of technical subtleties here. For example, it's these uniformization maps, you have to deal with them carefully if the geodesic goes behind the horizon and so on. These are covered in the paper, but I would rather focus on the results which are interesting in my opinion. Alright, so these are some results which are known earlier. These have also been seen in CFT calculations on also spin chain calculations in the XSD spin chain, for example. So at early times, just after the quench, so for u is my time, for small u, the entropy behaves quadratically in time. If I go to large times and large interval lengths, the entropy behaves linearly in time. And the proportionality factor is just twice the difference between the entropy densities. This expression has a nice quasi-particle explanation for it, which I'll tell you now. So the idea is that it's you can imagine like waves of entanglement flowing from both of these endpoints at the speed of light. So the wave front is the last point which is becoming entangled with everything outside. So it's like more and more of the system keeps getting entangled at the speed of light, which is why you have such a linear wave. This kind of quasi-particle picture was already known by Cardi and so on, and this was also verified holographically by Liu and Joseph.
So I made the same mistake once. The quasi-particle picture of Cardi et al. Does not work really for holographic symmetries.
That's
You have to
true.
use the entanglement tsunami.
Yeah, you have to use the Homolio entanglement tsunami. Yes.
I wrote it on the paper and the reviewer scolded me.
Oh, okay. Alright, yeah. At late times, the entropy behaves as a power law where the exponent is 3 by 2. And you might have noticed the L by 2 appearing here. The thermalization time is exactly L by 2. So if the interval has length L, it takes L by 2 time for that interval to be effectively thermal. Right, so this was the brief description of how the entanglement entropies behave. So what I can do is I can obtain analytics in each of these three regimes. I can analytically obtain the entropy and its derivatives at small times, at intermediate times, and also at late times. But generically for any time I can't do it numerically, I can't do it analytically, I have to do it numerics. So these algebraic equations that I mentioned, I can use like a Mathematica find root routine just to find these intersection points, and then I have the answer. So let me come to the main set of results. So the idea was to look at QNEC and see when it is violated or if it is violated. So if you recall, there are two QNECs, one for each of the null directions. So you can take derivatives of the entropy either in the plus or the minus direction. These two are plotted here. The plot A is Q plus, so the deformation along the plus direction. So I'm choosing an interval.
Sorry, where is the violation? How are you going to use this to check if QNEC is violated? I'm sorry, I missed something very
Alright, so I have the dual stress tensor.
Yes.
QNEC is just T plus plus greater than equal to some derivative of the entropy.
So dual stress tensor on the boundary.
Yes, I have the CFT stress tensor, and now I have the entropy from the HRT prescription.
Oh, I see. So you're not taking the QNEC in the bulk, but the QNEC in the boundary.
Yes, yes. Oh, sorry, I should have mentioned. Yeah. I'm looking at the QNEC in the 2D CFT.
I see.
And there would be no QNEC in the bulk because the matter is classical, so it would just be in neck. Right. Yeah. So the left figure here is one of the QNECs, Q plus. The right figure here is Q minus. You might notice an asymmetry between how they behave. That's because I'm choosing an interval from 0 to L, and I'm taking a derivative at 0. So one deformation decreases the interval, the other deformation increases the interval, which is the reason for the asymmetry. Already you can see, maybe you cannot see, but the initial value is just slightly below 0. So this parameter choice is already violated in there. What I want to emphasize in this figure is for Q plus, it's enough to just check it at U equal to 0. It never goes below its initial value. For Q minus, it might seem that it always just saturates to 0, but Q minus has a far more non-trivial behavior. It also has this non-monotonic behavior for other values of parameters. So Q plus, it's enough to just check it at U equal to 0. Q minus, I have to check it at all times and all entangling lengths.
What is the x-axis again?
Sorry?
What is the x-axis?
The x-axis is U by L. U is time, L is the
So
length of
0 is at the show.
just after the show, yeah. 0 plus epsilon.
Okay, but okay.
So Q minus should be checked at all times and all entangling lengths. I can only do that numerically. I don't have analytic expression at all times.
So you're saying Q plus goes negative a finite amount of time after the show.
Q plus, I'm saying if it goes negative at U equal to 0, you're done, it's violated. If it doesn't go negative at U equal to 0, it never goes negative after.
But are there shocks for which Q plus is negative for at a finite time after zero? At 0, QNEC is obviously not required.
Yeah?
But like at G, like for G,
Oh,
is
no,
it
no,
a
no.
finite time after 0?
No, it's not.
Okay.
I mean, if it's not 0, if it's not negative at U goes to 0 plus, it's never negative after.
Okay, then this.
So it's always this kind of increasing function. Whereas Q minus is can do anything it likes. So for example, here Q minus is positive at small times, but it violates later.
Do you have to worry about renormalization of the boundary stress tensor, or you just compute it?
Oh no, we do holographic renormalization and compute.
You have to do that carefully.
Yes, yes. So the usual scandalous kind of thing. Alright, so at early times, the stress tensor is known. I can expand the entropy in a Taylor series at U equal to 0. I get this nice analytic expression for both Q plus and Q minus. By early time, sorry, I should say, I mean that the time scale is much smaller than these mu plus and mu minus. So mu plus and mu minus you can think of as the inverse temperatures for the left movers and the right movers. Right, so this is the result plotted in a nice figure. So just ignore the dots for the moment. The black lines here, the solid black lines, are when this object is 0 and this object is 0. So they are when the QNEC inequalities are exactly saturated, just after the quench. These grey regions are places when the QNEC is violated at U equal to 0. Okay, I'll come to the dots later. So the x-axis is the change in mu minus normalized by the initial value. The y-axis is the change in mu plus normalized by the initial value. What I can do is just do a simple variable change. I convert the x-axis into a change in temperature and the y-axis into a change in entropy density. The definitions for temperature and entropy density are here. And what I see is for a given change in temperature, let's say you fix a delta T, I have a lower bound and an upper bound on the entropy produced in the process.
So you're not using here the quantum connected formula for the entanglement entropy also, right? You're not needing to use that.
No, but you mean the S bulk kind of thing?
Yeah, you don't need it.
because the bulk matter is just classical. Yeah.
So somehow isn't this on the boundary also just a classical energy condition? Why is it a quantum energy condition? Like on the boundary, okay, let me ask you a different question. On the boundary, is the classical energy condition clearly violated? Is the
No.
neck violated?
Neck is not right.
So so then why do you have to check the QNEC?
But classical RT formula is a contribution to boundary quantum entropy.
Yeah, yeah.
I know, but the classical RT, but on just there's a boundary stress tensor. Are you
No,
violating
the
some?
QNEC is proven independent of neck being true in the boundary, right?
I see. I see.
The statement is not like if neck is violated then QNEC has to be true. QNEC just has to be true.
QNEC just has to be true. Okay, but I'm just wondering if there's something much stronger you can say about the boundary stress tensor.
Ah.
Because the boundary stress tensor is behaving. I don't know. Okay. Is this just a classical system also on the boundary? Is the question I'm asking. But you're saying no.
No, it's in the sense that the stress tensor expectation is not negative.
Yeah. Is even the null energy condition
The
violated?
classical neck is not violated.
Is not violated.
No.
So it's really a classical system also on the boundary.
At the level of 1 point function, sure, but clearly the entropy is not.
And the entropy can be doing so this is really a test of how the entropy behaves, not really something funny about the stress tensor.
Not funny, but you should think of this as something about the state itself. It's a QNEC is a statement about the state itself. So for example, it's a derivative of the relative entropy of the out of equilibrium state with respect to the background.
Okay.
Sorry, in that graph you were saying you're talking about QNEC violation at U equals 0.
This figure you mean?
Yeah.
Yeah. So what I'm doing
U equals 0.
0 plus.
0 plus, okay. Is this also true at like 0 plus a finite value?
0 plus a finite value. For
because-
Q minus it is.
Okay, well.
Yeah. So and then these dots are from the finite time variation.
Okay.
So yeah, as I was saying, for a fixed change in density, I have a upper and lower bound on the change in entropy in the process. So this seems very similar to the bounds people have found in the quantum information literature. As I said, I'm not claiming that this is the same exact expression that I'm getting. It just seems very similar to what they found.
So what happens to your quenches violates QNEC?
What's the statement that there's no physical process that can lead to that? Or
Yes, so what QNEC means is that usually we have microcausality, right? If I take two operators which are space-like separated, they commute. QNEC is a statement about causality in modular time. So if I define the modular Hamiltonian for this state and evolve these two operators with their Hamiltonian, they would escape that causal dimension and start not commuting. So there's something sick about the state itself. And yeah, that means probably that this setup is not describing real.
So what do you mean sick about this? Like what is the sorry, can you just remind me what is the precise statement that's known about QNEC? You take any state, it has to be true?
No. You can write the statement for any state. Firstly, the relative entropy needs to be finite, otherwise you can't define it.
Okay.
That's the first constraint. You can define, for states which have finite relative entropy, I can write down the statement. But it's only been proven for states which have finite average null energy, which is like the integral of t plus plus, or t minus 1.
And then for any such state, it's true that the QNEC, you can, with very general conditions of the quantum field theory.
Poincare invariance and locality.
That's it.
Yeah.
You can prove that.
Poincare and Sean's proof is just that.
So in the black hole diagram, there is average energy finite.
He's saying the null energy condition is quite
No,
average.
you say you need the ANE to be finite.
The boundary ain't to be finite.
Yeah.
Yeah.
In the black hole diagram, they're finite.
Here it is not finite. But the holographic proof applies it.
So once again, so didn't you say that the null energy condition itself is satisfied on the boundary?
On the boundary it is, and also in the world, yeah.
So then why do you say that average null energy is not satisfied?
Standard formula proof requires that integral of t plus plus across a null line has to be finite.
It has to be finite, not just positive. It has to be finite. It can't be plus infinity.
Here it's infinity, but the holograph, there are different holographic proof that does it.
So the proofs are like in patches. They intersect in for some assumptions and they don't.
Yes.
Right, so the black lines are from the QNEC at small times. As I said, Q minus can be violated at later times, so I have to do numerics. So I just brute force sample over the the values of mu's which appear here and compute QNEC and check if it is violated or not. Unfortunately, there is no better way to do it. Analytics are really nice enough to do at small times. So these black dots are from QNEC violations at later times. So for example, from such a configuration. I'll tell you about the red line a little later. This also has something interesting to do about the holographic proofs. So if you recall, in my introduction, I said that QNEC is proven, as Subrat was asking, for Gaussian invariant field theories with generic assumptions. So why is it being violated in this setup? Also, there's a holographic proof which only assumes the bulk neck, so which is satisfied here. So why is QNEC violated here? Yeah. So the holographic proof by Kohler and others, they assume that the bulk neck is satisfied, which is true, and also that the bulk is a smooth classical geometry, which is the solution of Einstein's inequality coupled to matter. So our geometry is clearly not smooth. What goes wrong with the smoothness assumption is many of Wall's theorems about how these RT surfaces behave if you deform them, they fail. So this idea of entanglement wedge nesting, which is a key part of their proof, that fails. So entanglement wedge nesting says that if I take two subregions and one of them is included in the other, then entanglement wedges also have to be included correspondingly. That would fail under such a nullity problem because it's proven only for smooth space. So we don't know if this is true, this statement here. It is likely, I mean, as far as I see, this is the only assumption from the proof which is being violated. It is likely that this shock that I wrote down, I just plugged the metric in Einstein's equation and obtained a stress tensor. It's likely that this stress tensor can't be realized by taking like a scalar field and taking the limit where the source is turned on for a short time. So for example, there's this paper a while back by Tanay and Siraj. So what they did is they took ADS, they turned on a scalar field, turned on the non-normalizable mode, turned it on for a very short time, and they showed quantitatively that the bulk metric looks like ADS level.
And what is consistent that they only got delta J equals 0? Or?
Yes, so their calculation was only for when there is no momentum.
But did they also find a problem if they tried to change delta J?
I don't see anything mentioned in the paper at all. So this is something we are trying to do. Just do Siraj's calculation, just add momentum in both cases, and see if something goes
And
on.
is there any point to the graph something goes off for very small delta J?
For very small delta J. Yeah, so this line is delta J, the red line. So you just,
delta J.
yes. Sorry, it's delta J equal to 0.
Ah,
So the change in the momentum is 0. So
okay, so if you go to like the bottom, there's small delta J also.
yeah, small delta J.
Okay.
Yes, so you would see it quantitatively if I did this calculation. So this is something we're trying to do. Just repeat the calculation by adding momentum. Alright, so this was the story about the holographic quenches. How much time do you have?
7 minutes.
Okay, sure. So anyway, this is a bit more half-baked, as I said, we cooked it up a week ago. So the question is, like Ronak was saying, the holographic quenches are not quite the Cardi quenches. So one can try and repeat this kind of a calculation, just compute QNEC in usual CFT Cardi quenches and see if there are violations there, or if this is something specific about the bulk matter, as I mentioned. So one can try and repeat these calculations in usual quenches in CFTs. So what we tried is a couple of examples. One of them is famous global quench by Cardi. You take psi 0 to be the eigenstate of some Hamiltonian F0. You suddenly change one parameter in the Hamiltonian. Let's say you have an Ising chain and you change the transverse field instantaneously, such that the Hamiltonian now becomes H. And I assume that H is at criticality, so it's described by CFT in the continuum. And this is the time evolution. Epsilon H is just some regulator to remove high energy modes. And for this state, I want to compute the QNEC. So this is a global quench. Again, I'm injecting energy into the CFT instantaneously. Okay, so due to limited time, let me not repeat what you probably already know. You can just use the replica trick, and Cardi showed that entanglement entropies in these CFT2s are just correlation functions. So these can be computed using some universal expressions. Okay, the path integral looks like this. This is one of the sheets of the n-sheeted replica n-sheeted Riemann manifold you use. There's a branch cut along the interval that you want to compute entropy for, and so on. The stress tensor also can be computed in this setup. What you find is that the stress tensor is a constant, and that means the average null energy diverges. The Faulkner-Seyhan proofs only work for states with finite average null energy, excuse me, and finite relative entropy with respect to the vacuum. What they say in the discussion to the paper is that one should check if this proof can be generalized to more states which maybe do not satisfy finite average null energy. I mean, this is a fairly good state. I mean, the Cardi quench is not something crazy, it's an innocuous state, and it violates the condition that they've considered in the proof. So one ought to look at more general constraints one can impose instead of what they've done. So this is an example where the average null energy is not finite. However, the QNEC is satisfied. Now clearly one can't use this chain of arguments and say that I've proven QNEC for, I can't give examples and give you a proof, but I can give you counter examples. And a counter example is what is called a local joining quench. So imagine you take two icing chains separated far away, both of them in the vacuum, and I couple them at some time t. So in the CFT, I have to move CFTs on a half line and I couple them at some time t. And I assume the initial state is two vacuums. So initially it's vacuum, tensor vacuum, I couple them at some time t. After coupling, I evolve them with the CFT Hamiltonian on the full line. Again, let me not go through the path integral and the entropy calculations. The stress tensor has this nice form, it's a Lorentzian. Epsilon is a UV regulator you put in to regulate the path integral.
So doesn't the stress tensor diverge at the point where you couple the two things? Isn't there a firewall at that point?
Oh, okay, no, this is not quite what you see in this Almeri paper and so on.
So in Almeri paper, isn't this like the Rindler state, like thinking of the Rindler vacuum in Minkowski space?
Okay.
Isn't it like that? Because you had 0A cross 0D, so you compare the Rindler vacuum at time t equal to 0.
Yeah.
But the Rindler vacuum, if you computed the stress tensor, of course, would have a firewall coming out from the origin.
I think that there will be like a shock wave from
There'll be a
there.
shock.
There's a small amount of Euclidean evolution.
Yeah, I think the epsilon regulates.
that.
This is the epsilon is regulating that?
Yes, because I regulate, I mean, for example, I would, instead of evolving with e to the IHT, I would do e to the IHT minus epsilon.
So can you see the limit epsilon goes to 0 there is a shock wave? That also I'm not seeing.
Yeah, diverge is one of the...
Is this delta of W in the limit where the epsilon goes to 0?
Yeah, epsilon is the width of the Lorentzian.
I see, so this will give you delta of W?
Yes.
And W is which coordinate is?
It's
This.
one of the, it's a coordinate on the upper half. No, sorry, it's a coordinate on the actual.
So delta W equal to 0 is really the null. The null.
Yeah, W and W bar. W is like one of the null coordinates.
So it's delta. Okay,
Yes, this would be delta along with like right. So the average null energy, you can just integrate the Lorentzian and diverges. Again, it's like 1 over epsilon. Epsilon is some UV cutoff I put in to regulate the shock. What we find, you can do the replicated calculations again in the setup and take derivatives of the entropy. It's not a very sophisticated calculation. I mean, anyone can do this. Just take entropy and deform one point. This should have been checked a while ago. So QNEC is violated. So you can try and play around with different kinds of intervals. So for example, if the coupling happens at this point in space, x equal to 0, I can choose an interval which straddles the point of coupling, which is far to the left, far to the right, and so on. There are multiple such cases. In each case you consider, at least one of the QNECs is violated. So it seems that Faulkner and Seyhan's proof is not quite so easily generalizable to such states which violate the finiteness of average null energy. You might wonder if the other assumption goes wrong, if this state has infinite relative entropy. It does not, because people have shown that this state is actually in the identity sector, the CFT identity sector. So heuristically, it's like I'm taking two vacua, so it's like identity, tensor identity, I fuse two identities and I get something in the identity sector itself. So it's not that the relative entropy is diverging, which is why I can't do the QNEC. It is that the proof cannot be generalized to such a degree. Another interesting thing people look at, condensate theorists and others, is driven CFTs. So you can do time-dependent driving of CFTs. So recently, a paper by Meze and Jiang came out with, they constructed some holographic divergence in computer. But you can just do the calculation in CFT, I don't need to invoke holography. So the point is, for some time t0, I drive with the usual CFP Hamiltonian at 0. Then for some time t1, I drive with some driven Hamiltonian which has this enveloping function. And I keep switching between these. It's like a square wave which goes from h0, h1, h0, h1. Yeah, so let me not get into the details since I'm out of time. So for even such a simple driving protocol, QNEC is violated. This is the plot of the QNEC. It's negative. These dotted lines, to the left of the dotted line is the h0 evolution. This is the h1 evolution followed by h0 evolution and so on. These are, I'm just considering different kinds of cases, but in each of the cases I've so far looked at, QNEC is violated. A and E has to be evaluated numerically, and we find that it does diverge. So this also seems like a counterexample to the QNEC when this assumption is not. Okay, so I'll be done in a minute. Let me not waste time summarizing what I already said. Let me just tell you what I'm planning to do next. I'll be done in a minute. So, the setups we looked at were instantaneous quenches. At least in the holographic case, it's like I'm instantaneously changing the stress tensor. One can think of doing this kind of a quench slowly. So instead of a theta function change, you could do like a tan H and try and regulate the change. This could also be done using our uniformization maps. We are thinking of doing like a Riemann integral. You think of the tan H as like a sequence of shocks with small amplitudes and small widths, and integrate the tan H that way. So this can probably be done too. These setups are people couple like a SYK dot with a half-line CFT. These are interesting also for quenches. Although I agree with Subrat and other people's comments about how they may or may not apply to this literature about black hole information and so on, but I think you would also agree that they are reasonable setups for quenches. Yeah, so the question is what can I relax in Faulkner and Sian's assumptions, or is QNEC just restricted? I mean, does QNEC apply to a very limited set of states? That would be unfortunate, but maybe that is true. I mean, the set of states I looked at were fairly reasonable, but they violated this average null energy finiteness and seem to violate QNEC. Yeah, this is something we are just thinking about. Try and see what QNEC would imply on spin chains. So naively, you might think that this null derivative would just reduce to a spatial derivative. I take c goes to infinity. But if I take one direction of the spatial derivative, the interval shrinks. If I take the other direction, the interval grows. There is no known inequality on relative entropy for increasing intervals. You always define inequalities for relative entropy for quantum channels, which always reduce your degrees of freedom. So I can't think of defining a quantum channel which would increase my degrees of freedom in this. So the naive kind of translation clearly would not apply. So what we are trying to do is use something called a temporally leaf algebra, which is the lattice version of the Virasoro algebra, to do this null deformation. Finally, there are generalizations of the QNEC based on the Renyi relative entropies instead of just relative entropies. These are not as well established. They are proven in some free field theories only so far, as far as I know. One of the proofs was by Pradeep, who is a postdoc here. But we are also going to try and compute these Renyies in some of these. Thank you, that's all. Yeah, and this is the leopard.
Temporally leaf algebra is like about like composition of these boxes with like lines going through them.
Yeah.
What does that have to do with the Virasoro algebra?
Oh yeah, so on the lattice, if you just write down a local Hamiltonian, like sum over I, Hi, you can define the temporally leaf generators, and you take some scaling limit, take the lattice spacing to the small and so on. Ku and Cellular have some papers which show that they reduce to the Virasoro.
Oh, I see. And is there like an interpretation for the little lines going up and down?
Oh, those diagrams, I'm not sure. There is something, I think they have quite a lot of papers on it.
Also, why are you so hopeful about generalizing Faulkner-Sian? It seems like you just showed that QNEC is violated any time Faulkner-Sian or
but the holographic proof seems to be more general, right? It doesn't assume average null energy finiteness.
So actually the joining quench, yeah.
The joining quench also you could do holographically.
So what would the problem there be?
There also have a shock wave, so the usual holographic proof won't apply.
Joining quench is like the end of the world plane of the world. There's no shock wave, right? because the epsilon.
Oh, sure, so you
there's
yeah,
only
you
an
have the
entropy
plane
one
which
case.
is, yeah, then you decouple it. No, but in the bulk probably there would be a shock because the stress tensor jumps. For, let's say, before the coupling, the stress tensor is 0, and then after the coupling, it's this Lorentz zero.
Okay, there's a little bit of.
I think there will be some discontinuity. One way the Takyanagi realizes it, it's like some particle moving in ADS. So on the particle itself, it's like a
The
shock.
particle moving India, I think, is the inner world, right? The tip of the inner world.
Is it equivalent? Probably is. Probably is, yeah. But I suspect there will need to be a shock because the stress tensor jumps at just in the world just afterwards.
It has a weight, it's not a shock. In joining fields, like there's a weight because when you do the epsilon regulator, the stress tensor has like a non-trivial profile, not a data function.
Right.
It's smooth in the world.
Yeah, because of epsilon it's smooth out. And I'm not sure what because everything is. Yes. It could be a similar problem that maybe that stress tensor can't be realized with like a two-derivative theory compared to maximum.
So, overview question, I forgot, some point I missed the thread. So there was a lot of talk you had about checking the QNEC.
Yes.
But in the beginning you talked about this irreversible entropy change. How are these two related? I somehow missed the link.
Right. Yeah, the link is a bit tenuous, but right. So the point of the irreversible entropy change was in the quantum information literature. It seems that instead of just a zero lower bound, and it just has to be positive. They were both an upper and lower bound, both of which are positive.
On QNEC?
No, on entropy produced after it.
Okay.
So what we seem to find here is something similar.
Oh, I see. So you're saying somehow that maybe QNEC has an upper and lower bound.
QNEC imposes an upper and lower bound. So if you look at this plot, the y-axis is the change in entropy.
So you want to say it's not that T mu is larger than the second derivative, but T mu minus the second derivative entropy somehow is bounded above and below.
Oh no, so the claim is if you yeah, I'm just evaluating this and translating it in terms of temperature and entropy density.
So you want to say this quantity, which is somehow could be.
And there are two inequalities, the plus and minus. So one of them gives an upper bound, one of them gives a lower bound. One the entropy density. So instead of writing it in terms of these variables, I recast it as entropy and temperature. And I say tenuous because I'm not computing the quantities that the quantum information people compute. Although there may be a link because both are based on relative entropies. So that's the most speculation I will make.
What is classical clause and something you have seen?
Oh, just the second law from
But what is QNEC? That says quantum NEC.
Oh, quantum null energy condition, yeah.
What is NEC?
NEC is just kk is positive. K is any future directed null vector.
Okay. So in which there is a possibility of violation of that or?
Yes. So NEC itself can be violated just if you take a quantum state, expectation value of t can be negative. So the classical NEC can be violated. So then in the bulk, Wall and others came up with the quantum focusing conjecture. So in GR we know the classical NEC implies focusing, right? Light rays focus, gravity is attracted. If you have quantum matter, Wall came up with this conjecture called quantum focusing, which is some generalization. And some limit of quantum focusing gives you Q.
So classical focusing is related to Raychaudhuri equation?
Yes, exactly, just the right equation. Yeah.
And so it's just translated to the increase of energy or the increase of entropy?
Oh, so what you're right, classical focusing is just Raychaudhuri. Then what Wall does is he constructs a generalized version of the expansion. So the expansion should include the area term and also entropy of the bulk matter fields. If you do that correction, then you get corrections to the NEC which reduce to the Q.
And again, so what does it physically say?
For the holographic quench, it is telling me that, let's say you want to inject energy momentum into my CFT and see what states I can produce physically which are fine. It seems that if you want to change temperature, let's say by 10, the entropy cannot be changed arbitrarily. It has to be changed within some upper and lower bound. That's the, yeah.
The temperature should somehow approximately govern how fast or how slow.
Sorry?
with how fast you change the temperature, it will accordingly change.
No, how much you change the temperature will decide how much you can change the entropy.
Yeah.
But they can also be rewritten as bounds on the rate of growth of time. It's equivalent.
Some of these settings you mentioned, like coupling to Ising models and stuff, that sounds like something that one can do in the lab,
Coming to.
or are people doing these?
Oh yeah, I think it
Or
should be possible.
modeling it, or simulating it, or something.
You can simulate it on a spin gene. I mean, Cardi himself does it in calibration.
Okay, I guess some of these results come from simulations. Then.
No, the results I showed is just calculation, but they verify it also on spin gene.
Okay, so you can
Which
see
is why I
that
said
that
they're
means-
reasonable systems. I mean, I can engineer a chain here, not here. Not me personally. As well.
Yes.